Now we have the procedure to test a hypothesis, any hypothesis. The procedure is unchanging. All we are missing is the test statistic, relevant for the particular case we are interested in. In this unit, we will investigate the tests for the mean of a distribution. We have already met this question once before when we developed a confidence interval for a mean. The following two questions are interrelated. 1. What is an appropriate confidence interval for the mean of this distribution? And 2. Did the sample mean I just calculate come from a distribution that has a mean of x? X being some value important to me. To quickly review, the confidence interval for a mean is calculated by using the following formula. Mu is equal to x bar plus or minus z alpha times sigma over the square root of n. Now, in this case here, I've put in sigma. Of course, we won't actually use sigma. We will use s over square root of n, the sample proportion. The sample standard deviation. The second formula we use is mu equals x bar plus or minus t alpha times s over the square root of n. And we use this formula here if we're having a sample size that is smaller than 30. The second one is using a t-distribution for sample sizes less than 30. We graphed this concept with the following graph. We began with this. These are the individual x's. And that's some goofy distribution. Looks like that. We don't know what it looks like, of course. Here's the mean, and here's the standard deviation. All of these pieces of information are unknown to us. So what we do is, with the central limit theorem, we come down to the distribution of x bars. This is a sampling distribution. It has a mean, known as mu sub x bar, and it has a standard deviation, sigma sub x bar. Now what we've done is we will take a sample from the population up here, okay, and we will find it down here. Because we know that this is a normal distribution, central limit theorem told me so, I can draw this down here. And what I do is I take this x bar, this particular x bar, and down here I put a normal distribution on top of it. And that's what we have here. This is now our confidence interval at 0.95, let's say, confidence level, okay? Out here, we've got alpha over 2. Over here, we've got alpha over 2. And there is 1 minus alpha in here as our confidence level. And so what we've done is we've put a distribution on top of the x bar. All confidence intervals are the sample parameter we are interested in, the mean in this case, plus or minus something. The level of confidence we desired sets that something. It's right here, T alpha here, or Z alpha here. In developing a confidence interval, we do not have a predetermined interest in the outcome. We are quite simply asking our first question. What is an appropriate confidence interval for the mean of this distribution? Between what two values does the population mean lie? The second question begins with a number that we are interested in. For example, in quality control, did the student's average SAT performance meet the state requirements? Does the product meet specification that the percentage carbon in the steel matches the desired level to hold the bridge? Or is the weight of the cargo load too big for the plane to fly in bad weather? There is a number out there that matters. This forms the hypothesis. This is the null hypothesis, the status quo, the desired level. Graphically, we can draw this. Here is our sampling distribution of x bars. This distribution is normally distributed, looks something like that. Has a mean, and we're going to put mu naught in this case here. This is our hypothesized value. So h naught is mu equals mu naught. So we set the normal distribution of the sampling distribution on top of the hypothesized value. Then, under here, what we have is the z, because it's normally distributed. And what we're doing, in reality, is putting a confidence interval around the hypothesized value. Here's alpha over 2 here, alpha over 2 here. In between, we have our level of confidence, and what we do is we can calculate ZC. In this case, Z stands for Z calculated. It's equal to X bar, our sample mean that we found, minus the hypothesized value divided by S over the square root of n. This value here is called the critical value, and it's determined by the Z alpha. Okay? Graphically, we can see that all we are doing is putting a confidence interval around the hypothesized value of mu, the number that matters. Reading the standardizing equation, it says, how many standard deviations is my sample mean from the hypothesized mean here? Okay? If it's a long way away, we consider it unlikely. If we have a calculated value and it's sitting out here someplace, let's say, okay? Could it happen? Sure, it could happen. But it would be with a very low probability. And we set the probability so we know exactly just how unlikely this result is. Now we can reach our conclusion with this decision rule. If the calculated value of the test statistic is in the tail, we cannot accept the null hypothesis. It is just too unlikely. If, on the other hand, the calculated value of the test statistic is not in the tail, let's say in here someplace, okay, then we cannot reject the null hypothesis, the status quo. There are two last items here. First, if the sample size is less than 30, we do everything the same except we use the student's t-distribution. Nothing else changes. This is just what we did when we had confidence intervals, you'll remember. We used this formula here if the sample size was less than 30, and for the same reason. Second, it may be that our concern is two-sided. By that, we mean that there is something that is too large or something that is too small. Both of those matter to us. Imagine we run a bottling plant. We have a target of an average fill level of 8 ounces. We realize that there will be some variation around this target number. Too little matters, and too much also matters. This is a two-tailed test. Not all cases have risk on both the upside and the downside. Claims that are made are all of this type. I claim that my students are better than some other professors. This is a one-tailed test. My students must perform significantly better, say 2 standard deviations better, than some other group of students to sustain my claim. My claim makes me the challenger, trying to overthrow the status quo belief that both groups are the same. My claim is the alternative hypothesis. If my students perform less well than the other group, I lose before I begin. There is no left-hand tail in this case. Just remember that the level of confidence is still defined as 1 minus alpha. But now, all the alpha is in one tail rather than split between 2 tails. Hypothesis testing begins with a value of a parameter that is of interest to us. We fully expect that any sample will have variation in the sample mean value from the target value. In a way, we are asking a question that any 5-year-old would wonder why we went to college to try to get the answer. The bottling plant has a sample mean of 8.1 ounces and a target of 8. And we ask, is 8 different than 8.1? What 5-year-old would get this wrong? It is the variation in the sample that makes this a real question. Is 8.1 statistically different from 8? Maybe not. And this is the question that hypothesis testing answers for us.